All right, hi guys. I hope you guys are having a relaxing break. Sorry for the lack in communication. Well, midterms was a little stressful, and you guys had different times you guys wanted to meet, and I felt a little unfair to you guys if I made a meeting time that may not work for everyone, and I could not meet multiple days a week. So this is the next best option. So I finished my end of it. So all the lessons or tutorials, code, and everything is done on my end, including my project. So I'll just share it with you guys, and I'll give you till the end of May for you guys to finish your end of it, the project, if you'd like to complete it. We would like to see it because we'll display it in our club, and we might give an award to the best project, which could be anything from a nice little title to something more, maybe snacks, t-shirts. We'll take that when we get there. But anyways, so last time, which was probably early January, early February, we were talking about basically the beginnings of R, the syntax and stuff like that. And now I want to talk more about the data sets and what we're given. So you guys know this was all our library data, everything above here. This stuff down here is what I used for my project. We'll talk about towards the end of this. So just some basics. So I'm going to provide everyone this document. It's called big.rmd. It'll be uploaded and shared with everyone. So if you guys want to take a look at this code on your own time, feel free to do so. But a lot of this code I would not change if I were you guys, because it took me some time to work with this data set because it was really frustrating to deal with. So essentially this part is something you shouldn't change 100%. This is just taking the Excel spreadsheet that MedWish gave us and put it in a variable format, a data frame, if you will. This variable wouldn't change. My code wouldn't work otherwise. It's just making months a variable. So a little bit about the data set. So it is a spreadsheet. Let me see if I can actually find it for you guys. So it's a spreadsheet. I actually did a lot of editing to it to make it look readable. It didn't look like this. It was multiple Excel spreadsheets. I'll spare the details, but it looks like this basically in Excel. And when you upload it into R, it's a bunch of columns, a bunch of rows, and a months. And basically it is saying in January, MedWish donated 982 pounds of medical equipment to Molly Hospital's Safeland branch. And as you can see, a whole bunch of them, and they span for, I think, a couple of years. So it looks like it's going to be 5 years. So 2017 to 2021. This segment of code just made them all zeros for the missing elements. So if they didn't, MedWish didn't donate, they didn't put zeros, they just left it empty, which is a pain for R. And then this stuff is extracting the data from each of these sheets and combining all the Molly hospitals. For instance, what my code did, so let's see if I can, Molly hospitals is this code. This piece of code just says, hey, take the first column and make it vertical, or sorry, horizontal. And then this just says parse that spreadsheet to get the next two columns and add them to a little data frame, or you can think of it like a little mini spreadsheet called Molly Hospitals. And what it does is it adds up all these values, basically up until this column, Molly Hospitals. So these three, as you can see, a bunch of zeros here. So honestly, I could have done it by hand, but just to display in R the simplicity of it, I just did there. And yeah, and I saved it as an array called Molly 2017. I did it for every single hospital for every single year, which took me a while. Definitely might have some typos there, but it's fine. Okay, so now this stuff is combining the individual hospitals into a new data frame that is much more readable. And I call this recombinant data frame 2017 because I'm fancy that way. And I'm going to see if I can find it. Yeah, so it looks like this. It's a little simpler, less rows and much less text. So this is called recombinant. So I just combined all of the hospitals, combined all the branches into one, so less variables. And then this code, which I did for every single year, basically just labeled the columns because they had some icky names. Okay, this is the really crucial part of our code. So what it does is it makes an array or a data frame. And it says in this data frame, I want you to take the cumulative sum of every single one of the hospitals. So a cumulative sum basically says January or month one will be 982. February will be 646 plus 982, and so on and so forth. It'll take the sum of everything before it. So, and then I save them as something called cumulative sum recombinant. I was not really creative with the names, but you get the idea. It looks like this. So let no zeros, which is really important. And it makes it like graphing really easy. And I did this for every single year. And then this code is just if you're using ggplot2, you have to make it into two columns. I'm going to show you what that looks like, actually, if I can find it. I have a lot of arrays. I apologize in advance. And looks like I can't really find any of them, so that's fun. But if you can go, if you run this code on your end, and obviously if you want this to run, you're gonna have to change this to the path or where your Excel spreadsheet's located. If you have any questions, just email me about it. But that's the only piece of code that you will have to change because this is only for my computer. But anyways, so after this code, so honestly, you should not touch this code because this code has to stay the same for every project. Otherwise, it's really not going to work. Now, this stuff, as I wrote here, is pretty basic. So what this generates is it makes little plots. So this is called base R because I'm not using any packages for this. I'm not explicitly using it. Honestly, I don't even need this code, but anyways. So this just plots it. So I'm gonna do this. I'm gonna command enter on my end, and down here you should see a pretty little graph appear. These are the donations over time from all the hospitals. Looks cool, kind of boring, honestly. So a little more fancy is we need something called ggplot2. And as you can see, a lot more code is required. And if I go on this side, so this is the general syntax for ggplot. So it's going to be, you call ggplot, you're going to put the data frame, and you're going to use something called AES. From my understanding, it's like aesthetic, stands for aesthetic, where you set your x-axis to be your x variable. I want to say trucks, y, your dependent, miles traveled. And then you're going to have something called, so if you did this, and you did some, and you graphed it, it would show up. So this is the base. And then if you want to make it look pretty, you would use something called labs, which stand for labels. So title, x-axis label, y-axis label. Cool. If you do plus geom point, so by default, it'll plot it like little black dots. But if you do this, it'll make them blue dots and stuff like that. So that's called geom point. And then plus geom smooth. So what this does is it does a linear regression. I'm going to show you what that looks like by just running this command. And notice I put hashtag SE false. So by default, if you run this command, it'll show the 95% confidence intervals, I believe. Yeah, which you can see are pretty big because the data is really not linear or not linearized. So if we were to put that SE false command into here, what it would do is it would remove that. So a little handy feature. And if you're interested to figure out what the regression actually is, you would just run summary that. And as you can see down here, it'll show your R squared value is really high, or I guess really low, which means nothing really happened. There's no regression here. Okay, so that's that. So just some syntax. You can just do summary LM and then your X and then your Y. Interestingly enough, you couldn't just call the data frame, so I had to put as a vector. That's just some syntax. Honestly, for you guys, if you really want to get in the nitty gritty, I would suggest doing this. But if you know some Java, this would make it really simple. But you're more than happy to just copy. I'm more than happy for you to just copy paste my commands and just change them up, the data frames. So all you would have to do to edit my code, if you want to do this as the most basic thing in the world, is just copy my commands and change the data frames. So data, probably shouldn't change this one just because this is saying, hey, I want you to look in this big data set for this tiny data set. Anyways, so this is a t-test. You guys know what t-tests are. Show the little t-test down there. This is a chi-square test for independence. So this chi-squared approximation may be incorrect. If you guys know a little bit of chi-squared mainly works for smaller data sets, not really big ones, and doesn't really incorporate for a lot of variance that happens outside the variables you're interested in. Anyways, So chi-squared may not be the best approach to figure out if it's independent, if it's homogeneous or not, or whatever. I would use an ANOVA if you're too curious, if you really wanted to. Also, realize we're doing chi-squared between the cumulative sum of the amount of pounds donated from 2017 to 2018. I would honestly expect them to be homogeneous, but that's a different story. So correlation just tells you the R squared value, or sorry, the P value associated with it. And correlation test will tell you the R squared value, which, oh, I'm so sorry. That was the R squared value, and the P value is up there. P value is really tiny, so we're all good. Okay, so I did this for a lot of them. I'm just gonna show you some of the cool ones. So if you want to graph any of these and work with it, you're gonna have to do cumulative summation just because it gets rid of all the zeros, and that really messed a bunch of stuff up. So these are some of the nicer graphs I generated. So really nice regression, really tiny confidence intervals, and it's pretty linear. So I did this for every single one. It took a bit. Anyways, so going down here, I did the cumulative sum of the recombinant data frame, just some fancy language I used, which said, hey, the data frame I created from all the hospitals, well, yeah, use that and then color them by the hospital used, make the y-axis the pounds, x the months, and graph a line for every single one of those hospitals. Don't show those confidence intervals. Labels, these are just axes because I wanted to show 1 to 12 months, and that just shows how many like delineations of the x-axis would appear. So every 1, 4, like at month 1, 4, 7, 10, 12. So it looked a little like this, which looks pretty neat, pretty cool. Honestly, you could make this in Excel, but this is I'm touching the surface of ggplot. There's so many cool things you can do with it, and you can make them fun colors, play around with it. And if you're more interested, go to this website, which gives you every single command you can use for ggplot2. And some history about it if you're too curious, but I know the basics of it just because I don't have to know too much about it. All right, so that was the basics of R. So mainly people use R to make cool graphs, like using ggplot, which is a really famous package. And then people use the statistics capabilities, obviously, of R basics. It's called descriptive statistics if you're interested. But yeah, that's the basics. So yeah, this is just a graph I made, and then this is the code directly to make this graph. So now we're going to talk about machine learning. All right, because we're going right into it. I'm going to start with some theory though. So machine learning, if you've heard of neural networks, it's about the same thing. So neural networks is just a fancier version of machine learning. Machine learning is the older type. It's been around for like 30 years or something. So machine learning, there's a bunch of algorithms out there. Bootstrap aggregating, as you may have seen from the slide before. This is called random forests, and R is notorious and famous for its random forests. So there's really no simple way to go about this, but random forests comes from the idea that you have a bunch of decision trees, forests, haha, very funny. But so decision tree looks something like this picture right here, where you have those data sets, 2 red ones that are underlined, 1 red 0, and 4 blue zeros. So decision tree says, how many are red? Or is it red? Is an element red? The 4 blue zeros would go into the no, the 1, 1, and 0 would go into the yes. What are underlined? And I would go yes and no. That's a really simple decision tree. So computers, this is the core of it. So you have to realize that computers don't really do thinking, they do categorical analysis. That's the whole principle of machine learning, and specifically random forests. So a little more complex, and hinting back to the term random, they're going to make hundreds, and I mean hundreds of decision trees that incorporate every single variable. And so say you have a data set and you follow this heuristic, and maybe this decision tree says, I don't know, 1, 0, 1, a whole bunch of them say this. What machine learning says is they go through every single decision tree they made according to your code, and they average it. So the prediction, in this case, they're not averaging. Some average, some don't. It depends what your code says. This one just says predict. So this one says, hey, it looks like there's going to be a couple 1s and 2s, 3 zeros. The overall prediction will be 1. And the easiest way I can explain this is, what if you're like flipping a coin, or better yet, gambling, because flipping coin is pretty fitty. But if you're gambling, you play one time, you may have like a 55% chance of winning. If you play 10 times, maybe you're getting like a 59. If you play 100 times, you're going to get a 99%. This is what the whole point of random forests are. The more trees or decision trees you make, we're talking like thousands and thousands of them, the better your accuracy at predicting your true outcome. And that's the amazing part of machine learning. That's why you use super complex computers and stuff with big processing power and stuff to predict. The real life example I can think of is I'm currently working on a project at the clinic where I am saying that your blood pressure, whether you're pre-hypertensive or not, can predict your later risk of mortality from cardiovascular events or incident cardiovascular events, the correct term. And I'm using, I believe, 200,000 decision trees across, I think, 459 variables. So yeah, random forest can get quite big in my computer. This is the same computer I use for that project and it works fine. So if you're interested in it, Case actually provides you high speed, I wouldn't say supercomputers, but really freaking fast computers if you want to use for data science. They're available through Citrix Workspace, if you're familiar with that. Anyways, so random forest, cool, more trees, more accurate. Okay. So we're going to get into something called bootstrap aggregation. So it's a technique called bagging. I'll refer to bagging from now on. So these decision trees, they can predict really well, and small changes in your data set can actually cause significant different trees. So what I mean is if you change one variable in 1,000 variables to like 0 instead of 1, it could affect, I would say, maybe 10% or 20% of the trees you generate. So that's really good, actually. So what we do is we do something called training and testing. We train the machine and then we test it. So in your data set, let's actually go back to our data set. Okay, let's go to this one. So bagging says we're going to take the first 3 rows and we're going to make that our training data set. So we're going to tell the machine, hey, I want you to train your forests on this set. These are all you're given. And then we're going to split the rest, maybe rows 5 through 12, into your testing data. So we're going to say, hey, random forest, decision tree computer, I want you to if I'm give you 5 months, Hatchet Fish Hospitals, weird name, I don't know, but gave 3,000, you gave 3,009 to MedWish gave 3,009 to them, that, and we left pufferfish, tau, and tetra blank. How much would you predict they have? And the machine will go, okay, and they'll predict it. And the more trees you get, the higher your accuracy. I'll just show you some code I was running earlier before this. I have it. I apparently had a mean squared error of 3.595, like period. That's a percent mean squared error. What it's saying, sorry, it's not a percent. Oh my God, what am I saying? It's saying that usually the machine is within 3.595 of the true value. So what it does, it bases its stuff off the training data set, and it goes to testing, it predicts, and then it looks at the actual value and it says, hey, I'm 3.5 off. That's pretty good. This is not for this is for my project. And you'll see that accuracy is pretty cool. And then this percent variance says how much of the variance from the 200 trees I generated is explained. So if I made the trees 400, I'd expect this distance to shrink from 100. So I'd maybe say 75 of the variance would be explained if I have 400 trees, but that would take forever. So not for this project. All right, back to the data set. Back to the station. So yeah, so this is what an actual decision tree looks like. So it says, hey, what if I have features 2 and 3? So variables, maybe X and Y, and these are Z and W. And I made this decision tree, left node, right node. For these purposes, it's not really important unless you're doing true data science, but what it is it's like 2 of the most opposite outcomes from that data tree, from my understanding. And what it says is if you combine these random forests together, you would get an overall decision tree once you combine all the variables. So each decision tree only combines a couple, and when you make a big one, it should be super accurate. That's all it's saying, at least from what I understand. So let's go to some machine learning code. So I call this machine learning VIMP. So VIMP stands for variable importance plot. There's some pretty cool ones out there. I think I made one down here, right? Yeah. Okay. So let's looking at it. So this thing just says, hey, I want you to sum up everything. I want you to move the months column. This stuff is just some housekeeping. And this command says, I want you to normalize the data in respect to one. What does that mean? So it means that I want you to have values from 0 to 1 for everything except for the dependent variable, the pounds of crap donated by MedWish. Not crap, I'm so sorry. Stuff. Yeah, so it's called cum sum recombinant. It stands for cumulative sum recombinant, same thing. So I'm just gonna pull it up so I can give you. So it looks like this. So I averaged it. It should obviously be 1 for each one because I would expect the final summation to be 1. Anyway, so it looks like this. And the reason I did it like this is because it actually enables the machine learning to go faster because smaller values, it's easier for the machine to do its job rather than have to go to so many decimal places. And plus, I doubt they have that far decimal points for, stuff, pounds donated or whatever. So also got to realize the machine learning can do so much. It is using math at the end of the day. So you're going to have for instance, you could have maybe you're predicting the amount of people a company has and has 2.2, machines aren't that smart. So we can, and what I do in my projects actually just round off, but there's better ways. And this is just a dependent variable I kept as big numbers. Okay. So I can actually run this code at the same time, I believe, because I do the data set. But so this is what we call our training samples. So as I mentioned, we create the training and testing data. What this command is saying is I want you to go through this and partition the data such that 50% of the data set is used and 50% isn't. And this is just saying, hey, this is the index number or the position in our matrix. I want you to cut the data off. And this is just generating those two training and testings. Honestly, this looks really complex, but I truly, I think I copy pasted this from my textbook a long time ago. I've been using the same code for a long time. So yeah. Oh, and full disclosure, I would say maybe 90% of this is not my original thought because these are come from papers, theories, textbooks, tutorials, but this is from my understanding of it. So this is obviously tailored to this project. I would say no one writes their own code for this because everyone has to use packages. You would have to be nuts to write your own machine learning code, truly insane. Anyway, so this is the model. So we created the training and testing data. So as you can tell, we're doing bagging, but we're also going to do random forests. We're going to do method 1, which is the method you use if your data is crappy like this. You don't have much data points to use. What this does is saying, hey, we're restricted by our data set, so please make the best tree you can. Or trees. So this command trains the trees on the data set. This code honestly means nothing to me. All it says is that my data is coming from the training data set. So if you change the testing, you would do it in testing, which makes absolutely no sense to me. And this just says, hey, generate 10 trees. And yeah. So that's the model, the trees we're going to make. But wait, I mentioned we're not just making trees because trees don't tell us much. All these trees are telling us is, hey, we have a model for you to do, but what about what would you do with the trees? And this is where VIMPs come in, variable importance plots. So this is a variable importance plot. What it looks like is it says, hey, so I didn't change any of the plots because this is just for a class. I'm teaching this project. I'm not actually submitting this to a paper or nothing, but so the y-axis are the hospitals. So tetra, blah, 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 bagel, ideas, stuff like that. And this is the, we can think of this as the relative importance where things on the far right are 5-fold as important as things at 1, and then 0 means they're not important. They're inconsequential to the trees. So when I say the decision trees, they actually tell you how important a variable is because when they generate the trees, they're like, hey, if you go down this branch that goes to this variable, does that really matter a lot? And they found that these hospitals, Port Huai, or where the hell you pronounce that, and Plecostomus, these are pretty low on the importance versus Tetra. They said, hey, almost every decision tree had a branch that's split into a lot of categories for Tetra. That's pretty important. That's the giant importance. And you can see down here, this is from a different one. So these two pictures from different parts of my R code. This is showing the textual interpretation where it says, overall, Tetra seem to be responsible for like is 100-fold times as important as bad example. Tetra is 5 times important as Plecostomus and stuff like that. These are just two things saying the same thing for different data sets, but this is not generated without this. So this is the tough part. So this won't actually work if you'd use our data set for MedWish. So this is just saying, hey, what is the model? And this saying, hey, I want you to take that predicted trees and I want you to model that and predict our testing data. This, honestly, if you were to do this again, I would not change any of this code. I would just go back and change. Where is it? I would change this part, which says the data set I'm using to actually do the machine learning. Anyways, so blah, blah, blah. This is the stuff. This code just tells us some details. It tells us how accurate the model is. I got 0. Maybe you guys will get something higher than that if you run it because all computers are different. But yeah, with large data sets, you'll find this is more accurate. I'll show you for mine. This tells you the variable importance plot. Oh, sorry, this just tells you the mean error. This tells you the importance, and this stuff is inconsequential. This just tells you the textual stuff I showed you in the next slide. These two are important though. So this generates the model variable importance plot. This just tells you the numeric things in a cleaner format. Just like that. Cool. Is that anything else? Cool. Okay, let's go. Cool. Okay, so I hinted we're going to talk about forests, which are pretty cool. Yep, so looks like that's more code. I did this for every single year so you guys can see what actually changed. And you can see actually it's really cool because the importance for hospitals or what the computer deems as important to the amount of pounds donated changes for every year for every hospital. See, like Pencil though, Pencil Hospitals is doing pretty baller, you know, pretty important. So the interpretation of this, so when I look at this variable importance plot, if I change the axes to be more valuable, colors and title, what this says is Hospital Nocera is the most important hospital to MedWish's overall donation. What it's saying is that if MedWish were to go forward, they should focus their resources on maybe other hospitals like Vestron because they may need more, and maybe decrease the amount to Nocera, or maybe focus on Nocera because they seem to be really needing more stuff. Interpretations vary. That's truly a human part of it. So this is called VIMP new. As you can see, this code is actually quite tiny. 1, because we did all the housekeeping code above, and 2, because this is purely using random forests, no bagging at all. You may say training and testing. This, I like to say, is not so much bagging, it's just training the trees, actually. So this code does stuff. I have it outlined on the right-hand side. The same general idea, just you know, I wouldn't change this part of your team. This is the training data. I would change this data frame. Anything you see CumSum or like recombinant or capital DF, or you see 2017 or stuff that looks like I wrote it, probably change that for your data set or whatever you're going to use in the future or for this project. Anyways, when you do this, you're actually going to get this as a random forest, and this is terrible actually. So because our data set's so tiny, they only could explain 63.72 of the variance, or you could say the p-value is going to be like 0.37, which is not significant. Anyways, that's all that kind of says. It says I made 500 trees and there were only 2 variables at each branch, which is not good, but something. And this has the error. The error is in terms of e to the power of 8, which is ridiculously high. But as you can see, the overall error decreases the amount of trees. The x-axis, the amount of trees used, 100, 200, 500. The error kind of decreases and plateaus, as you can see. So more trees, better for, better for us, but lower error. So this important part of trees is tuning. So you can tell the trees, say, hey, be better. And what it does is you can think of it maybe as a little bias. It tells the machines to take a look at the training data and to retrain the trees and take, and it's like called pruning the trees. I think is the best thing I call it, not tuning, but pruning. You're cutting the branches that are inconsequential. And honestly, that's not terribly important. This just tells us that how many trees have 2 branches, 3, and a couple have 4. The higher the branches, the usually better for a model. And it generates another VIMP. And if you compare this VIMP to the other VIMP, you'll find the x-axis makes absolutely no sense. Once again, think about this as fold importance, like, 2-fold, 3-fold. But the pencil still ranks high. So these models, even though they're generated from different means, different code, different theories, this one's using forests, the other one's using bagging plus forests. You can see that this one actually, they say the same thing at the end of the day. Maybe a little bit different. And you can see, you can run this code every time and you will get a different graph than I do. And there's a way around it though. So if you type in the command set seed, I don't know, 100, if you set this and I run this, you will find that every time I run this, you will get the same thing. Let's see if I run it again, what happens? Oh my God, it's the same thing. Now, what if I set the seed to 101? Run this again. Oh my God, it's different. What if I do 400? You can keep doing this. You'll find you get different values because on your machine, there's a whole theory behind it. My computer science teacher explained this to me a while ago, but if you're testing your data and you want to see, hey, is my code even working or am I doing something wrong every time? Do the set seed function because every time you run the code, it'll be the same. But every draft I'll make here, it'll be different from the one you have because my seed, I'm using air quotes if you can't see it. My camera's not on, but I'm using quotes. Everyone's seed is different for their computer unless you go ahead in your code and say type set seed. Anyways, that's some programming crap. All right. Yeah, variable importance plot. Oh, cool stuff. Okay. So my project's pretty cool, honestly. So, oh, sorry. It's 3 p.m. here. I don't know why I'm tired, but anyways. So my whole project, let me explain this stuff to you. So my project set uses data sets, and I'm actually going to pull it up for y'all. I think it's pretty neat. If I can find it, honestly. So this was called hospital info. Okay, that's one of them. This is called disparity. Okay. I have 2 data sets. The first one is called disparity. So I am a psychology major. It's something I'm interested in, honestly. It's pretty cool. So in psychology, there's a whole bunch of stuff that, matters towards mental health and stuff. And that goes to something called the social disparity index. It's called SDI score in my data set. So I'm going to provide to you my code that made this project. You can incorporate however you want. This code that I wrote for my project, 110% original. So feel free to reuse it. You don't have to cite me or anything. I don't really care. But the data sets I use were taken from universities and the government. So please try not to repurpose it. And if you're going to do that, please re-download it and don't get me in legal trouble, please. Thank you. So yeah, this is a data set from I think University of Wisconsin-Madison or Michigan. I can't really remember, but yeah, it has population, county. So these are called FIPS codes, FIPS. It's like a zip code, but universal. Population, scores, black percent, black in the community, or not percent black. I'm so sorry. It's the relative abundance of African Americans compared to any other race. They can get pretty low or pretty high. I can't remember what they were, but something. I knew it when I did the project. So this is the non-employed stuff like that. And, oh, here we go. Percent. Okay, I got it. So yeah, it's pretty self-explanatory. Ooh, okay. So this is a little teaser of what's happening, but this is the data set. The data set did not include occurrences or MedWish impact. Those are 2 things I wrote. I added the data set in R. So yeah. And then this is cool. And the second thing is hospitals. I took a data set of every single hospital in the country. Anyways, cool stuff like that, right? Anyways, let's back to my code. So I'll explain it to you because I didn't comment it because why, you know? Anyway, so I did this. I imported the data set. I converted all the counties in that hospital info, all the ZIPs, zips into FIPS codes. This took forever. I would not recommend doing this code on your own. And then I took this says, hey, I want you to count how many occurrences of every hospital occur in each FIPS code. So what it says, hey, if I find so our FIPS code is 39035. So I want to look in the data set. How many times you count that? That's how many hospitals there are. That's logically sound, you know. I took the disparity index and I put it into R, and then oh, I guess that code's not important. Anyways, ignore that. So this just said, hey, make a new column. Anyways, this code's not important. All this code basically did is count how many occurrences there are. Anyways, not important. Okay, so now with our final data sets called disparity one. Let me see if I can find that. So this is not it. Not it still. Anyways, okay. So I made this. Oh my God, still not it. Ugh, whatever. Okay. So what I did to my data set, oh my God, where'd I put it? Okay, here. I made these two columns, right? Occurrences and MedWish impact. So I went and I told my I used my R code to put the amount of occurrences in the correct FIPS code. So FIPS, whatever, 17045, I had two hospitals. Some have NAs because not every FIPS code will have a hospital, or it's just not listed or stuff like that. So I use the amount of data that's available. It's a limitation for all of this. It says how much data is available. Cool. Use it. And then I went ahead and put the impact of MedWish on communities. They're there. They're somewhere. They're present in this data set. I just don't know where they are. I think I have one for Cuyahoga County and one for county like Franklin or something. It's like Akron. Anyways, that's MedWish impact. And I have a whole bunch of NAs. And so what I told R, I use a fancy technique called imputation. So what imputation does, it generates these forests, these random forests, and with these missing variables for what it knows though. So it'll have a whole bunch of forests and maybe only 10 of them include the variable that are missing. And what it says is, hey, use those trees and I want you to guess what goes in the empty spots. And I fed them SDI scores. So what I'm saying is, hey, machine, based off the social disparity index, I want you to fill in how many hospitals there could be in the area based off what you know from every other county, and then how much MedWish, did for stuff and things. And then here I just rounded because I just wanted to, round. I don't want like stuff. Anyways, that does not really do much. Oh, I did set seed here. Cool. What did tree R part do? I have no idea. I just know I needed this. Oh, it just says I want you to make that tree, which I'm gonna use later on. The decision tree. It's trees. Then I just made that. You've seen this code before. This is just fitting a tree again, making that tree, doing that stuff. Blah 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 blah. Same code from before. I literally just changed the data set. I'm reusing my own code. And I made this cool little graph which tells you the variable importance for all the variables. So it looks like, so I did a regression for the hospital occurrences. So I told the thingy, the computer, hey, for what variables are important in the data set from your imputation, from your decision trees that you made, what seemed the most important to go towards the amount of hospitals that occurred in an area? And this went okay. And I found the percent non-employed. No, non-employed, not unemployed. The people who choose, oh my God, I actually don't know the definition of non-employed. Are you kidding me? Oh, okay, that's what non-employed means. Okay. So yeah, people not employed, they do stuff. And that they're the percent of seem to be relatively more important than anything else. The county location seemed to be important. The amount of African Americans actually seem to be really important, as well as the social disparity index. So it seems, you can make your own conclusions. I'm not a really good psychologist, so I can't, or sociologist, I can't say what that means, but what that means to me as a data scientist, it says the percent unemployed, the location, the percent black, the population, the social disparity index seem to be more important than the amount foreign born, the high school dropout rate, the people with no car. Those are the relative importance of variables towards the amount of hospitals in the area, because I did. I termed the available occurrences and how many hospitals there were. Alrighty, then I'll put the MedWish data in here. This shit just puts the MedWish impact, MedWish pounds into the data set again. And I did imputation, so the software kind of predicted how many pounds MedWish could donate, to other places, maintaining the same level, or for what MedWish could donate based off what they're doing to Cleveland. Note the words could. I don't know what the data set is here, but I'm sure if you run this code, you'll find it. It may take a while. And then what I said, which is pretty cool, I also rounded, so I had whole numbers, integers. I said, hey, so this code says a couple things. So I'm going to start from the beginning. This is used for parallel processing. So what this says is your machine has how many of those things that computer processing, I don't know, the processing units, CPUs. It tells it, hey, so I actually have 16, but I also didn't want my computer like totally freeze while I was writing this code. So I said 8 so I can, like watch YouTube and stuff. I would suggest we're limiting this down to like 2, I assume, for most of you guys, because you guys have laptops, but whatever. So if you have, anyway, so I would make this 2 for you guys. If you're confident your computer has like 4 cores, 8 cores, take that number and put it there. So I have 8 cores, I put 8 because you have 16 cores realistically. Anyways, I'm no computer scientist, but yeah. So this part says, hey, make 2 empty data frames, and this while loop tells you a couple things. So I am primarily experienced in Java, so I'm familiar with this. I would suggest looking up some basic loop implementations, such as for loops, while loops, do if for each, if loops, a whole bunch of commands out there. But yeah, what this says is, hey, I want you to 1,200 times erase the social disparity index. I want you to erase that value for 1,200 counties. And then I want you to imputate. I want you to guess what that social disparity index is based upon how much MedWish could possibly donate to that community. And I want you to do this 5 times. This is so I could run this code while I was waiting for this Zoom meeting to start and while I was running and stuff like that. I, matter of factly, actually ran the code a couple hundred times. And here I ran this code for this loop 20 times. 20 times 5 iterations of 200 trees. That's 1,000. I ran this code for 20,000 trees. This code in R, I went 5, 5, and 200. So that's probably 5,000 times. So my model is, I'm no mathematician, but I think 4 times better. I don't know. It's exponential. So exponentially better is the model I did on this paper, which took me, I think, half an hour on my computer to run. Anyways, we're going to close out of that for now. So I ran this and I saved it as a data frame called disparity differences dip, but accidentally opened. And this tells us how much our disparity changed. So positive numbers are really crappy. What that says is, wow, if MedWish donated, it would take away resources like from our community that we might need somewhere else, or might use up too much manpower, resources, whatever. And it says, hey, it'll increase 48 times or 48 more than it actually is. And then, some are actually negative, which is awesome. I think there are more negatives than positives, which is good. But what this says, the MedWishes might not be one in every city, and this just says stop parallel processing before my computer shits itself, you know? And this is a ggplot code because I think ggplot's neat. Anyways, I accidentally flipped this. I'm actually gonna just do that before I forget. So cool. Yeah, so this is a change in social disparity index when MedWish resources are directed elsewhere. So say we're directing MedWish resources to a county with a, I don't know, 20 zip codes, you know, whatever. It says, hey, maybe this one right here, this dot where my cursor is going to be down here. This just tells us the social disparity index change if MedWish were to move its operations or focus its energies on different zip codes, different hospitals there. As you can see, some communities welcome it, some wouldn't. This is not definitive. This is just machine learning algorithm. And you can definitely run my code again, but I'll just show you the things. The mean it's pretty nice, actually. It's explaining a lot of the variance. So I believe I had some code that told us how good it was. Maybe not. Well, this is telling us in the beginning when we imputed that we had very, very, very low variance, very high mean squared errors, but that's fine actually in this case. But anyways, this graph, as you can see, these two graphs are very, very different actually. There's some tiny, tiny differences. So for instance, if we look down at 20,000, it looks like this is a little more up than this one. This on my PDF right here is the most accurate one because I ran 20,000, or sorry, a lot of decision trees. Anyways, this was my project. I basically said that a MedWish should focus a resource in a different city. So I guess I should interpret this. So machine learning and the correct interpretation would be, obviously these axes should be flipped, but when MedWish were to direct its resources to different zip codes, the social disparity index would change according to this graph. And it appears that most are negative. Some would actually stay near zero, as in their MedWish impact wouldn't help nor be like harmful to the city. And knowing that the percent non-employed where the location and the percent African American seem to be a very big impact factor of the amount of hospitals that occur, MedWish should focus their resources in communities that may have more unemployed individuals and stuff like that. Anyways, that seems pretty common sense, but this machine learning algorithm goes further. It says that in communities that maybe are more Hispanic, they don't need many resources or need MedWish's resources as much for people, populations that have more African Americans. So there's a whole bunch of interpretations that exist in this. I just focused on the most general one because I am lazy. I wanted to finish this project for you guys so you guys can work on it. But yeah, that was my project. And I hope you guys really enjoy this because I had some fun writing this code. As you can see, I had a lot of fun. I actually wrote 552 lines of code. So just to clarify, this that says R my project, feel free to just delete it if you guys don't want it. This stuff up here, that's called Vimp old, Vimp new, feel free to keep it if you want this as reference code for your project. Or if you just want it later down the road, you know, if you think my code's really cool and stuff, so you want to save it if you get more interested in this. Basic R crap, that's like my housekeeping, making basic ggplots, showing you the extent the language can do. And this stuff up here is just some code that you might need. So this is, if you want to run my project, I would suggest installing and getting these two packages. And yeah, once you're done, you just hit knit and knit to PDF and you'll make this cool thing. Is 47 pages, but most of it's just, yeah, just graphs and stuff. So I'm going to send everyone all this stuff. Obviously, the PDF isn't perfect. If you have 2 long lines of code, it'll knock it off down there. But yeah, I hope you guys enjoy this. And let's see, is there anything else in this presentation I wanted to talk about? Nope, that was it. So general things about this. So what I hoped everyone would gain from this is how to use R. Hopefully you guys know how to use R at this point. And if you don't, there's so many great research out there, and R is not a hard language. Like most of it's intuitive. This is just an equal sign saying, hey, make everything 0. This thing store a data frame as that. These tell you an index, like row by column. So if I have 1, 5 here, go to row 1, column 5, transpose it, which means make the rows columns, columns rows, put it as a data frame. This stuff, honestly, to me, reads like a language, and I hope it really does for you guys too. I'm not a computer science major. I hate computer science. I hate data science. I hobby in it because I think it's neat sometimes, but it's a pain in the ass to code. But even I understand it. Um, because I guess I found the English in it. So I would suggest thinking about like that. Try reading it like a sentence, and truly you will understand this code better than even I could. And hopefully you guys win like a Nobel Prize or something. But okay, so more about this. So my goal for everyone here, Jesus Christ, what the hell is happening? So my goal for everyone is to have their own project. Maybe not as long. Maybe your project as simple as saying, I am going to find 10 hospitals in the country and I'm going to figure out how many donations they need for MedWish to be better. I said I'm going to do that for every suburb, but whatever. Or you could even expand what I'm doing. Maybe you want to identify the most important variables once MedWish is in play. Like, is MedWish a more important variable in determining the, I don't know, STI score? No, where did that? Hospitals, like will increase the amount of hospitals. You could even do a time sequence. You could take data from 2015, 2019. Those are two data available for the STI index and say, hey, MedWish between 2015, 2019, looking at Cleveland, has improved his SDI by decreasing it. What if you did a time series analysis for every single county, which would just be as simple as expanding my code, finding the data set from 2015, putting it in here, imputing it with the same data, changing what data sets to use, because remember MedWish has everything from 2017 to 2021, and doing that. But there's some pitfalls with data science that you guys need to be aware of. This analysis is a prediction. Predictions have significance values. This is a 0.95. Backtrack actually. Sorry, I need to find where I set the confidence interval. I mean, I guess that's close enough. So that's like I'm not really familiar with the percent variance. Oh, wait, variance is convertible. So that'd be close to a 0.99 R squared value, I'd say. No expert in that. But and this is not the same because this is averaged, not average, but it's additive. I don't know how to explain it, but the significance of this is close to 0.99. But this is called post hoc analysis or retrospective. We're not editing the data, we're simply observing upon the trends that already occurred. So we can't give any prospective claims such that MedWish will affect the SDI index. We can say they could affect the SDI index, but more research needs to be done. But it's super important exploratory, what do you call it, data science, because I know a lot of people who are currently working on stuff like this at the clinic or currently in businesses or even at UH. I'm aware of one psychiatrist who's currently doing this upon a data set of parents completing a survey for parental stress. There are so many uses for this software, and you can change it for any variables because these variables are non-discriminate, meaning as long as you have numbers, fuck it, you have words, you got words in here, same thing. There's a fun thing in R called factoring. It says if you tell R factor this data set and has words as variables or words as like instead of numbers, it'll take those words and make them numbers. And then you won't even know it because they'll do the analysis upon the words. So if you have like 10 words that have red, like 10 words that are like that have the word, no, what do I say? If you have 10 words and like two of them are like the word red, three are the word green, it'll say, hey, let red be one, green be three, do some analysis, and then I'll tell you, hey, red, green. And you'll do the same machine learning. Machine learning is quite versatile. And this code I gave you is so general, you can use it for anything you'd like. It's just some pitfalls though. Again, you need your data set to be really big. The data set I have used for disparity indices, that is, I would think 30,000 rows of 30 variables. So it's close to 1 million entries, which obviously I didn't generate myself. I took from a website as public use, free use, whatever. So yeah, I hope that was helpful. I hope this project is comes in handy for you guys down the road because it's definitely working out for me, I'd say. I'm doing a MedWish project on it. So yeah, something I'm interested in. I hope you guys find it too interesting. And if you want to know more, feel free to just Google random forests, bootstrap aggregating, machine learning. And if you're more interested, look up neural networks. That stuff is wild. And if you're more into the more clinical side, such as I am, feel free to look up Kaplan-Meier survival plots. And if you're interested, it's actually in R. So I'm actually gonna go back to R here. There should be a package called survival. Yeah, survival analysis, serve minor. This is using clinical science. There's also Cox hazard regression analysis. No, hazard ratio, whatever. It's another thing they use in clinical science. What that Cox thing is, it's a multivariable regression. It's very cool. It's a type of machine learning in itself, honestly. And machine learning is used in a whole bunch of fields and stuff like that. So yeah, I hope that was helpful, guys. And let me know if you have any questions. If you could just email me. And yeah, have a great rest of your spring break.